Hello and welcome to my presentation entitled UK View on 5G for Mobility. My name is Bob Banks and I work for Vodafone Group Research and Development based in Newbury, England. I'd like to start by giving you some general information and background about Vodafone Group. As you can see from the slide, Vodafone Group is not just a mobile network operator, but a leader in technology communications with a worldwide footprint through its local market operating companies and its partner network program. The local market entities are either fully or majority shareholder owned by Vodafone Group, whereas for the partner market networks, Vodafone has no shareholding but a commercial business agreement in place. This agreement can cover many different aspects, but a couple of examples are the use of Vodafone services and the Vodafone brand. Moving on to the topic of 5G, a key thing we need to understand at the very start is what do we actually mean when we talk about 5G. 5G technology contains a suite of different features and functions, some of the key ones of which are shown as examples in the red speech bubbles at the top of this slide. However, some of these capabilities are also able to be delivered as part of a 4G network. Let's have a closer look into the table on the slide. The table has three different 4G, 5G network configurations down the left side, and across the top, different 5G features or functions. If we look at the first row in the table, the 4G radio access network plus the 4G core network configuration, or option 1 as it is referred to in the 3GPP specifications, then we see that capabilities like radio access network slicing, quality of service, ultra reliability, and edge computing can all be achieved and do not need 5G. If we move down one row in the table and bring into the network configuration 5G new radio and the associated dual 4G, 5G radio connectivity, also known as option 3X non-standalone in 3GPP speak, then we can start to add the ability to deliver ultra low latency. Going to the final row, where we have a 5G NR radio access network and a 5G core, which is 3GPP option 2, standalone, then we can deliver a yes in all of the capability boxes. The reason for showing this table is to demonstrate that a lot of the required connected vehicle services can be delivered using a 4G technology-based network, as per shown in rows 1 and 2. As these can deliver the required features or functions. Yes, there are perhaps some connected vehicle services that require the full 5G network, or row 3 in the table. And when we look at automated vehicle services, then the full 5G network becomes required even more. So how is 5G being rolled out in the UK? 5G new radio rollout is happening in the 3.4 to 3.6 gigahertz band. And once the outstanding spectrum auction of the 3.6 to 3.8 gigahertz and the 700 megahertz bands is complete, which is expected to be in the Q1 timeframe next year, rollout will commence there as well. Note also that all of the existing licensed mobile bands are technology agnostic. So refarming and use of these bands for 5G new radio is also possible as an operator requires. At the moment, all commercial deployments are non-standalone, with standalone systems being deployed for test and trial purposes. Also, there is a lack of commercial terminals at the moment that can support the standalone configuration in Europe. From a service perspective, enhanced mobile broadband is the key driver for 5G new radio deployment, and hence focuses on the areas of high demand like towns, cities, and major transport hubs. However, some early deployments for the likes of Industry 4.0, mobile private networks, and connected and automated vehicles, and health purposes have commenced and are expected to increase going forward. Focusing on the connected and automated vehicle space, it's become apparent that a new ecosystem is required to deliver this. The changing trends in the automotive industry listed on the left side of the slide together with the new requirements from the road operators listed down the right side, bring together a number of key existing industries shown in the middle circle that need to work together to ensure successful delivery. This new ecosystem is now beginning to coalesce, and such organizations as 5G Automotive Association are helping to bring these industries together and drive this forward in a coordinated and aligned manner. In addition to this new connected and automated vehicle ecosystem, new business models are required to support sustainable commercial investment by the industries. Whilst a degree of interaction in the delivery of services has been occurring for a number of years, as shown by the diagram on the left, the move to connected and automated vehicles requires a move to a more fully cooperative model, as illustrated on the right. The level of dependency of each industry on the others makes it very difficult for any one industry to commit to investment without having visibility of the resulting value chain and its associated business model and revenue flow. Vodafone has been working together with another major network operator and technology supplier on the architectural aspects of the infrastructure for connected and automated mobility. The outcome of this work is shown in this slide. Starting at the bottom, we have the classic connectivity layer. This is where all relevant transportation-related data generators and consumers are located and connected to their relevant services via a high-performance network. You can see in this drawing examples such as variable message signs, roadside weather stations, smart parking, etc. For simplicity, this drawing only shows such a network being an LTE 5G network, but this could also be a wireline or fiber network. If we move up one layer, we arrive at what we are calling the mobility cloud. This is a layer still within the network operator and where the network operator provides platforms through which it can deliver its own services, as well as hosting applications of third parties and delivering their services, both from a point much closer to where the data is being generated and consumed. This is where edge compute platforms would be located, together with such example services as geolocation and data analytics or video analytics, etc. Sitting above the mobility cloud is the traditional central cloud, where back-end services are located. This central cloud can be located in the network operator or outside the network operator environment in the back-end servers of the likes of road operators or vehicle manufacturers or mapping providers, for example. Let's look at an example to illustrate how this architecture can be used to deliver connected mobility services. Here we have the existing service of telematics data. Today, each vehicle manufacturer uses a mobile network subscription to pass the telematics data from its vehicles through the network operator and out to its back-end systems. Here they can analyze their vehicle data as well as sharing relevant parts with third parties who can provide additional services back to the vehicle manufacturer, and also, if applicable, back to the vehicle. In this model, no data is shared across vehicle manufacturers to enable larger data sets to be created and the corresponding improvement in analysis and with road operators. Introducing the mobility cloud architecture enables the existing telematics data service to continue as is, but also enables the intelligent transport system messages, namely the CAM, the Cooperative Awareness Message, and DENUM, the Distributed Environmental Notification Message, as defined by the European Telecommunications Standard Institute for Europe, ETSI, coming from all vehicle manufacturers' vehicles connected to the network operator, be brought back over a cellular-wide area connection and collated into a super data set in the mobility cloud, while still adhering to all security and privacy requirements. This super data set can be made available to relevant road operators for use in their back-end system, either separately or in combination with other data obtained from their own existing physical traffic sensors, for example, traffic cameras or induction loops, etc. However, the mobility cloud can, through the use of edge computing, do real-time analysis of incoming messages to identify anomalies in vehicle flow, as well as supporting a longer-term analysis to identify vehicle flow trends and characteristics. The edge computing-based applications doing this real-time and periodic analysis can be either network operator provided or third-party provided, for example, a road operator. As the number of vehicles on the road that are using such CAM and DENUM increases, this architecture delivers a larger and stronger data set, and ultimately could replace the need for road operators to use physical traffic sensors. So is this mobility cloud architecture just a paper exercise? Well, no, it's not. Moving to this slide, Vodafone is in the process of implementing this architecture in the West Midlands area of England, in conjunction with the regional council there, the West Midlands Combined Authority. WMCA consists of 7 local councils and, as a result of its mixture of over 20,000 miles of urban, suburban and rural roads, enables Vodafone to test its architecture on a multitude of road types. A series of use cases will be undertaken over the coming months as a result of equipping several hundred vehicles that spend a large proportion of their time travelling within the WMCA area. For example, fleet vehicles, public transport vehicles, taxis, etc., with cellular wide area CAM and DENUM capabilities. The dataset generated, together with the real-time and periodic analysis, will be available to the existing WMCA traffic management system to show how such information can be used to complement their existing traffic flow data, strengthen their traffic management capabilities, and perhaps ultimately become the main source of traffic flow data. Thank you very much for listening to my presentation. Goodbye.